This is Surveying 1, Lecture 11. And in this lecture, we will be discussing angle and direction measurement. This is a topic that will be continuous over several lectures as we introduce more and more complexity. Let me begin by talking about angle measuring instruments. In the textbooks that we use today, you typically hear the word total station, but if you go back in time, you'll hear the words transit or theodolite. And then, if you really go back in time into the 19th century, for example, you will also see compass. And this is not the compass that you might have used in the Boy Scouts. This would be what's called a surveying compass that actually had a tripod attachment at one time. Before that, it was mounted on a single staff called a Jacob staff, and they would actually measure bearings or directions with the compass, and most of them had sighting vanes so that you could sight down a line, and then from that determine directions of lines directly. Of course, once you have the directions of two lines, as we discussed in the previous lecture, doesn't matter what those directions are, then you are also able to determine the angle between them. Typically, however, today, with a theodolite or with a transit or even with a total station, it's more typical to measure the angle and know the reference direction, the meridian, to relate those angles to the meridian, and from that determine the directions of the lines. So direction measurement would be done with a compass. Angle measurement would be done with transit, theodolite, or total station. In both cases, what we are really eventually interested in is direction measurement or computation or determination of the direction of lines. So let me talk about what the basic instrument would be if it is a transit, a theodolite, or a total station. We'll talk more about what those three things are or what distinguishes them a little bit more here. But these all have some similarities, and those similarities are in this conceptual diagram. So in this conceptual diagram, I want to first start with the telescope. They all have a telescope that you sight through to observe whatever it is that you're observing to determine the angle between 2 points. The other major thing, however, is to note that this instrument has a vertical axis, meaning that you rotate the telescope around on this vertical axis. To be able to set the instrument up accurately to measure horizontal angles and vertical angles accurately, what we need to do is align this vertical axis with the direction of gravity, which in surveying is the definition of the vertical. And so to do that, we have some kind of a leveling system, and the most basic of that is some kind of a bubble in an enclosure which is usually made out of glass. The glass is curved on top so that the fluid, which has a bubble in it, will always tell you that you're level when that bubble is centered in its enclosure. We usually refer to that enclosure as a vial, and in the case of a transit, that vial is sometimes called the plate vial. That's because there's a horizontal circle and a vertical circle, and it used to be that the circle was called a plate because it was made of steel, usually plated with silver, and then had graduations engraved upon it. Now, to make the leveling system work, it needs to be adjusted such that its horizontal axis is perpendicular to the mechanical vertical axis of the instrument. So even if this instrument was leaning over let's say the instrument is leaning over 2 degrees, then the plate vial axis, or the main vial, leveling vial axis, would also be inclined 2 degrees, except the vertical axis is 2 degrees out of vertical, and this plate vial axis is now 2 degrees out of horizontal. As you may remember, the horizontal is always defined as being perpendicular to the direction of gravity, or the vertical. So by attempting to get this bubble centered, what you are doing is making the leveling vial horizontal, the leveling vial's axis horizontal, and then if it's properly adjusted, that would mean that the mechanical vertical axis of the instrument is vertical and therefore aligned with the direction of gravity. So that's the basic part. What I haven't shown here is something called the leveling base, which sits down here. And the leveling base can take different forms, and when we go into a discussion of transits, theodolites, and total stations, I'll talk about that a little bit more. I just want to acknowledge the fact that this thing does exist and is something that you should be aware of. So you have the leveling base down here. So if you follow these arrows, we have 2 circles. So the circles are basically like protractors. You need a protractor to measure angles on a sheet of paper to determine the angle between any 2 lines on a sheet of paper that intersect. And we're doing the same thing, except we're doing it on the surface of the Earth. So there's a circle, and you're seeing the edge view of the circle down here. This would be the horizontal circle, so that when I sight at different points, I am swinging my telescope through a horizontal angle. We also have a horizontal axis, which is made in the factory to be perpendicular to the mechanical vertical axis of the instrument. And again, by definition, if everything is properly aligned, namely that you properly centered and adjusted level vial, then the horizontal axis is going to be truly horizontal as well. And then mounted on that axis is the vertical circle, so that as we raise and lower the telescope, we can now measure angles in the vertical plane. So you notice I've called this the trunnion axis. Trunnion axis is very common around the world. It's actually known by people like your instrument technicians who work on your instrumentation. Not as common among American surveyors. You often refer to it as the horizontal axis or the telescope axis. And so that's the basic arrangement of the component parts in all these measuring instruments. Some of these instruments have more, some of them have less, and the newer ones have a lot more complexity associated with them. And unfortunately, sometimes people don't think about what the essential elements of these instrumentation are, and that's why I'm taking the time right now to go through those. So here's a transit. This is actually a very old transit, because the vertical circle, you notice, is only an arc of the circle. It's not a full circle. And in newer transits, you would see an entire circle. There is a horizontal circle. So kind of looking at the edge view, and you see these things that look like plates. They're actually frosted glass to allow light to come through, but cutting any direct light, such as sunlight, that might fall on the viewing window. So there's a metal circle, as I said, and there's a viewing window through which you can look at the circle to read off the graduations. And you see here on the opposite side, exactly 180 degrees apart, that same frosted glass on the other side, so that you can look at it from over there. It's hard to see in the lighting of this photograph, but here is your level vial. Of course, here's your telescope axis here. You can imagine a vertical axis because there is a bearing in the center around which the instrument rotates. This would be the center of the horizontal axis here. And down here, it's mostly cut off in this photograph, is the leveling base for this particular type of instrument. Going into the details of exactly how that leveling base works is not so important. And there's various clamps and other things that can be used. I should also point out that on transits, you typically had another level vial over here. And this level vial was used to more precisely level the telescope if you wanted to set it up in a horizontal orientation. Generally, that telescope was that vial was generally the most sensitive, even more accurate than the vial that's on what we call the plate vial. Now, here's a theodolite, and these pretty much went out of style in the 70s, 80s, and 90s. That's the 1970s, 1980s, and 1990s. And these were much more compact. Telescope was a lot shorter, much lighter, and much simpler to use. And even here, you start to lose some of the detail that's visible in a transit, and that's why I start with the transit. So up inside this part of the instrument, which is often called the yoke, and that's Y-O-K-E, not Y-O-L-K as in an egg, but these are sometimes also referred to as the standards, because the standards basically contain the horizontal axis on which the telescope is supported. So you have a mechanical vertical axis that passes through here, and the horizontal circle is inside this streamlined looking truncated cone. You can see the shape of the vertical circle right here. So the vertical circle is also enclosed, very few exposed parts, but sitting down here, you can't really see it in this photograph, is a level vial that goes from right to left as you are standing at the eyepiece end of the telescope. I probably don't have to tell you that this is the telescope right here. There's the eyepiece. This is the objective over at this end. And here's the leveling base. So this is what's called a leveling base for a theodolite type of instrument. And I intentionally picked this photograph because it doesn't have something called a tribrach. So we'll get to that in the next picture. Something else that is worth pointing out on this instrument is something called an optical plummet. So this is a telescope. You actually place your eye over here and you look through the optical plummet, which is basically what we call a folded telescope. So there's a mirror or a prism right here. So your line of sight goes to the prism and then comes straight down the mechanical vertical axis. It's actually hollow, and this telescope allows you to observe the ground so that you can use it and the reticle built into the telescope to center the instrument directly over a point. Now, with the older instrument, the transit, there's usually a hole on the top of the tripod head, and there was room for a hook to be attached to the base of the transit directly in line with the vertical axis. And what you would do is hang a plumb bob by its string, and that's how you'd ensure that the instrument was centered over a point by having a physical prolongation of the vertical line, namely the plumb bob string. As you can imagine, when you have wind and other things happening, a plumb bob can be somewhat inconvenient to deal with, And so one of the innovations with the theodolite was to have an optical system to enable you to center the instrument over the point. Won't get into the complexities here, but the leveling base is actually easier to level up the instrument. There are a set of controls, I won't go into all of these, that are used to point the instrument at the targets that you're observing, various clamps and so forth. Here's what's called the vertical clamp, the horizontal clamp, the vertical tangent motion. You can't see it, but this is the end of the axis for the horizontal tangent motion. This instrument also had something else called a circle positioning knob, and these are all a little bit of throwbacks because they're not used today, but I'm just pointing out in case you have run into this terminology as you look at different instrumentations, or if you look at older textbooks that still refer to these kinds of things. So finally, I want to move to a modern total station. So modern total station is basically a theodolite, but where, oh, I forgot to mention, so because these circles are enclosed inside these cavities inside this metal body, on the other side of the instrument is a little aperture and a mirror that lets you send light into the instrument so that you can read the circles, the vertical circle and the horizontal circle. And the circles now, instead of being made of metal, they're made out of glass, and there's graduations on the glass. And this generally allowed a lighter instrument and allowed the ability to observe the angles to a much higher degree of precision. So these instruments also have circles of glass, but now they have electronic coding of different types. Sometimes there's an optical reading system, sometimes there's a magnetic reading system, and the kind of graduations placed on the circles vary depending on the technology used by the manufacturer. But here's the eyepiece of the telescope. Here's the objective of the telescope. Here's an inset view showing the other end. Now the telescope itself has this box-like shape, and that's because built into the total station is also the distance measuring capability. So you sight once and observe not only your angles, but also your distance. So you have controls on the side of your instrument. On the base, which is hard to see, there would be an optical plummet somewhere. The optical plummet is the sighting device that lets you see the bottom, and here's the leveling screws on the leveling base, and of course there's the tripod. And to make it a little easier to take in and out of the box is a carrying handle, which is one of the ways you can carry the instrument. And then today, most of the time, a modern optical station, a modern total station is going to have something called a data collector or field controller, which is a way using Bluetooth technology or some other way of communicating to be able to operate the instrument to perform mathematical functions and to collect data without having to manipulate the instrument keyboard a lot. And in this particular instrument, it's also motorized, so you don't even have to touch it. It actually turns itself and can be used to sight the target. Some of these have cameras built into them so that on the display of your field controller you can actually see what is being observed and actually align the crosshairs on the target without actually looking through the telescope. In fact, we've often talked about having a blind telescope, meaning that there's no eyepiece, but to my knowledge, nobody has yet invented that, because there are plenty of times when you need, either for calibration reasons or some other reason, the ability to still sight through the telescope with the human eye. There is a display on the instrument and a keyboard, but it's fairly limited, and you do most of the um, interaction with the instrument very often through the field controller or data collector as it's called. So there are various kinds of total stations. When they were first introduced, they pretty much were basic. They measured horizontal and vertical angles. They had an electronic distance meter, and they could do basic math functions. Some very simple things like calculate coordinates, calculate elevations maybe, and a few things like that. As time went on, they had more and more, so that the mathematics on them became more and more advanced. And now many of these devices have very specialized programs. Sometimes you can buy additional programs to do very specific surveying related functionality. There have been also some improvements to the technology. I haven't talked about this yet, but to measure distance, you typically cite a retroreflector or prism, and we have now also EDMs that do not require a reflector. It'll simply send out a strong enough signal that it can reflect off anything to measure the distance. We also have scanning total stations, and a scanning total station can be set up. Remember, they're motorized, so it can be set in reflectorless mode to simply take an observation every degree, or every half a degree, or every third of the degree going across, and then to move up a little bit and take observations again and again. So this is called scanning mode. Some of you may be aware of things called laser scanners. Well, they work like laser scanners, except they work a lot more slowly, but in a pinch can help you get a lot of data over a fairly large area when you don't have a scanner available. And finally, because you have this motorized capability, you have these so-called robotic total stations, which can be programmed to do a number of things, including follow a prism, for example, and to even take observations automatically, depending on how you have set up the programming on them. So there's a total station. This is a different brand, so it looks a little bit differently. There's the optical plummet on this particular instrument. The leveling base is down here, the leveling screws. Forgot to mention on the previous picture, but it's also visible here, is the concept of a tribrac. And a tribrac is basically a leveling base on which the instrument is placed, but which can be detached. So you can leave the tribrac attached to the tripod, and you can remove the instrument from that leveling base. But same kind of thing, you have a telescope, you have controls on the side, you have a display, you have a keyboard. This happens to be an antenna for communication with the remote field controller, because what we have here is essentially, with a robotic total station, one person surveying. So the person holds a prism pole. It has an omnidirectional prism, and the instrument, once it has acquired lock on the prism, can then follow the survey around. And so the person in charge of the survey effort is now the person holding the rod, and there's nobody actually operating the instrument as it goes about its techniques, as it goes about its observations. And as the surveyor moves around, here's the field controller attached to the prism pole, simply presses the read key or take a measurement key or compute this function key, and depending on where the data resides, the data is used to compute things and can be used to turn the instrument from right to left or up and down, to either set out new points or to measure the positions of existing points. So just to review some of the things we've talked about, there's the tribrac or the leveling base that you should be aware of now. that is a critical part of the instrument. Then there's the alidade, and it turns out the alidade, if you go back through these instruments, is pretty much everything above the horizontal circle. So this is all the alidade. This is the part that rotates around the vertical axis. So the alidade here is everything above the vertical axis. The alidade here is everything above, I'm sorry, in my previous note I said vertical axis, I meant horizontal axis, or the horizontal circle. And again, here's the alidade. So the alidade contains the telescope, contains the vertical circle, and all the controls, but it doesn't turn with the horizontal circle. The horizontal circle stays fixed. We already talked about the horizontal circle. We've talked about the vertical circle. We've talked about the telescope. So let me say a few words about the last item on this list, which is the compensator system. So in my schematic representation, I talked about the level vial. The level vial is the crudest way of setting up the instrument so that it is properly aligned with the vertical direction, so that its vertical axis coincides with the direction of gravity. Well, it turns out instruments are not perfect, people are not perfect. And nature doesn't help you out, because small fluctuations in the position of the instrument with respect to the vertical can change as the instrument warms up and cools down, especially if the sun is striking it directly, because you can have what's called differential heating going on, differential heating and cooling. And so very, very early on, and this is one of the reasons why, let me go back to the transit picture again. This is why we have a telescope vial. So this is the telescope vial, which allows you to level up the instrument or the telescope very accurately. And why is that? Well, it turns out that to measure horizontal angles accurately, you need to do a pretty good job of leveling up your instrument. But to measure vertical angles accurately, you need to do an even better job. And so basically, the plate vial is designed to be of sufficient accuracy or sensitivity to allow you to align the vertical axis of the instrument with the direction of gravity, such that you will not have significant errors in your horizontal angle measurements. But it turns out that's not enough for very accurate vertical measurements or vertical plane measurements, angles in the vertical plane. And so the telescope vial was added for that reason. Once we get to the theodolite, it turns out there is the equivalent of a telescope vial, but they mounted it over here on the standard of the instrument. I won't go into the details of why that was done and how that was a benefit, but essentially it allowed you to again measure angles in the vertical plane more accurately than simply by leveling the plate vial. Once we get to these total stations, people had discovered in the older technology, the theodolite technology, ways of using gravity in a similar way to the way you use gravity in an automatic level, to be able to be able to detect gravity and apply that known direction in some fashion to the vertical angle reading system to improve the accuracy of the angles measured in the vertical plane. So today, of course, that's done electronically, and that system is called a tilt compensator. used to be called a vertical angle compensator because it only helped you measure vertical angles accurately. Well, as it turns out, if you're sensing gravity and you can improve the vertical angle accuracy, it turns out you can also improve horizontal angle accuracy. So it's no longer called a vertical circle compensator, it's simply called a compensator system. And we have two types then. We have a single axis system and a double axis system. And what is that? Well, a single axis system is essentially a vertical circle compensator system. But if you have a double axis system, it's also improving the accuracy of your horizontal angles. It's improving on the human factor in centering a level vial. So you center your level vial as best you can, but this dual axis compensator system, the double axis compensator system, can even improve the accuracy of your horizontal angles. Now, to conduct the process of angle measurement, just like much of surveying, it's an art and a science. And the more experience you have doing it, the better you get at it. And that's one of the reasons why in Surveying 1 and 2, we have field labs, not because you may be, as a surveyor, operating surveying instruments for the rest of your life. You may have other people working for you, but you can't direct them, you can't analyze the data, and you can't catch blunders unless you have hands-on experience this process. And so that's the reason why we bring experience into the angle measurement. It's not always there in the field, but the way surveying works is you have someone with experience, or maybe more than one person with experience, who's able to determine whether that process was carried out well enough for the job at hand. And I just wanted to add, because we have no plumb bobs, it makes setting up and observing angles a lot easier and a lot faster than it used to be, but that doesn't mean it's necessarily foolproof. And that's why the experience comes in, and the ability to approach angle measurement as an art and a science is a really important part. You simply don't do it by a rote method. All right, so to measure angles on the surface of the earth, it's very similar to the way we measure angles on a sheet of paper with a protractor. First of all, we need to know where those lines are. Now, the lines may not actually be physically marked, but typically we'll have 3 points. And once you have 3 points, there's actually 3 angles, but certainly there's one angle that can be measured easily by simply connecting 2 points to the third point. And what I mean by that, if you didn't follow me, is that we have a second angle over here and a third angle over here and so forth. But in this case, we're just discussing the first angle down here. Let's just, for sake of convenience, call this point A, call this B, and call this C. So if you wish to measure angle BAC, that's how we designate angles. The point at which the angle is measured is the middle letter, so angle BAC. The first thing we do is we take our protractor, if it's a sheet of paper, and place the protractor so that the center of the protractor is on the point where the two lines intersect. Well, in angle measurement in the field, horizontal angle measurement in the field, you have to do exactly the same thing. And that's the reason for having the plumb bob in the old days and now the optical plummet. So you have to place the optical plummet such that the vertical axis of the instrument passes directly through the point on the ground. So the other thing that has to be done is that you need to level up the instrument. You need to level up the instrument to make sure that at least the two-axis or single-axis compensator system can go to work. And that means that in the process of leveling, if you've already centered the instrument, it will throw off your centering. And as you recenter, you'll find that the recentering throws off your leveling. So it takes some experience, it takes some attention, and it takes some understanding of the actual manipulation of the instrument on its tripod to be able to do this efficiently and quickly. I've seen people do this where they've taken a half hour to get the instrument leveled and centered, but in reality, if you know what you're doing, you should be able to get it done in 2 or 3 minutes. The next point that also takes experience as well as art and science is the actual sighting. So we have different kinds of targets that we observe. I won't go into this here, but we'll talk about it more from the textbook reading point of view. But what you have to do is you sight through the instrument, you have typical set of crosshairs, and you have to place your crosshairs on the objects you are sighting. These objects might be prism poles, they might be chaining pins, they might be what we call traverse targets, they might be a whole number of different things. But being able to precisely and consistently place your target on the points is important. Now keep in mind, just like this point here is on the ground and you have to extend vertically to the instrument, these points are probably on the ground as well, B and C. So you somehow have to extend them up vertically, opposite to the direction of gravity, so that you can properly measure the horizontal angle. And then finally, there's the reading and recording part. You can't measure these things. That's useless unless you can actually read the angle properly and you can record it. Now the reading has become a lot easier because you simply read whatever is on the display. But it turns out it's not quite so easy because you can't always set 0 when you sight the point B, so that whatever you read when you sight C is the actual angle. You may actually have 10 degrees, 4 minutes, and 10 seconds, and you turn the angle, you have something else. You actually develop a technique or a process or a thinking process, which is whatever my final angle is, I subtract my beginning angle. Even though most of the time it may be 0, it's not always 0 for all kinds of reasons. And then, of course, recording it accurately is important. Again, with total stations, we may do that electronically, but recording it accurately is also an important part, and that's where the blunders come into the picture. All right, so one of the things that people need to do when they measure angles is find ways to make sure they've done it properly. And an easy way to do it would be to simply measure the angle a second time. But what surveyors discovered a long time ago is a process called closing the horizon. So here's those same 3 points, and we just measured this angle. But one of the things we can do is also measure this angle here. And if we measure that angle, we know that those 2 angles need to add up to 360 degrees. So it helps us catch blunders, and if there's small errors, it gives us a really good handle on what those are. So knowing what closing the horizon means is really important, and knowing how to do this in the field is just as important. So let me talk about, before we move into closing the horizon, another important step. When we measure angles with an instrument like a total station, there are several inherent instrumental errors that can be there because no instrument is in a perfect state of adjustment. So we do something called reversing the telescope. That means as we sight through the telescope at a target, and then we sight at another point through the telescope at the target, what we do now is we invert the telescope and turn it around so that we can sight the telescope again and measure it with the telescope in what's called a reversed or upside down position. So there's several terms that I use. Sometimes you'll see plunging, you'll see reversing the observation. Flopping the gun is a colloquialism. You'll never see that in a textbook, but you may have heard about it, or you certainly will if you continue in a surveying career. Generally, what I tend to use is this term here, observing in phase 1 and phase 2. So phase 1 and phase 2 actually come from the days of the transit, where you actually knew on your instrument exactly where that vertical circle was. And it used to be pretty traditional when you're looking through the telescope with the telescope right side up, that the vertical circle would be on the left-hand side. And so they used to often call that face left. And then when you invert the telescope, the instrument turns around, so now the vertical circle is on the right, so they used to call it face right. So if you read all the books, you'll actually see face left and face right. But once we started to make these things more and more streamlined looking, it's actually hard on much of the instrumentation we use today to tell which side has the vertical circle. So now we simply refer to it as phase 1 and phase 2. And when you look at the instrument, it's pretty clear. You can usually figure out sometimes the writing on the telescope, the branding, and so forth, the marks will all be upside down when the telescope is reversed. So when everything is right side up, we call it phase 1. When everything is upside down, we call it phase 2. So you need to know that observing in phase 1 and phase 2 has the effect of removing a whole number of errors that exist in the instrumentation. We won't go into these in detail, but you need to realize that there are errors always in angle measurement, and the only way to remove most of them, not all of them, but the only way to remove most of them is by observing in phase 1 and phase 2 and then taking the average of the result. And that, by the way, is in addition to doing something like closing the horizon. Now, you don't have to always close the horizon. We'll talk about that here in a second. So here's a set of typical field notes where we have closing the horizon. So we have set up at this center point over here, and we start by recording the angle from B to C. And what we do here is we then invert the telescope. That's why it says reversed reading, and measure another angle. And then what we do is we average the two and report what the mean is. And don't pay too much attention to the actual angle values in here, because the instrumentation you may be using in your labs may have a totally different set of readings. But certainly this is one set of readings that is possible with the modern total station. And so you take an observation with the telescope direct, you take an observation with the telescope reversed, and you average the two. You do the same thing from C to D, and then from D to E, and then E to F, and then from F to B. So there's 1, 2, 3, 4, 5. But those 5 angles we know need to add up to 360 degrees. So you see the check that's been done over there. They only missed by 2 seconds. Clearly this is not a student, because most students wouldn't do quite that well. But nevertheless, it's illustrative of the kind of check you should do whenever you close the horizon. Now in this particular case, we happen to have 5, but remember, when we measure an angle, anytime you measure an angle, there's always at least the other angle. So we also, just like in leveling, refer to back sights and foresights. So where we typically measure the angle by calling this the back side and this the foresight. Now, after we finished measuring that angle twice, we can now say, okay, now I'm going to back-sight this angle. We use different color. So now I'm going to back-sight this angle and then whip around over to here and call this my foresight. So I have a second angle. And then if I added those two up, they should also add up to 360. So there's always a minimum of 2 angles you can measure whenever you are in angle measurement mode. It just so happens in this particular setup, there were 5 points of interest that could be observed. So you go ahead and observe all 5 and make sure that they all add up to 360 degrees. Now, we have something called traversing, and we'll talk about that more in a future lecture. But most surveying involves the measurement of a closed figure. We often refer to this as a polygon, but in surveying parlance, we often call this a traverse, and the process of measurement traversing. And traversing simply means that we measure these angles. So you see angle A, angle B, angle C, angle D, and angle E, and so forth. So these angles are measured, and they were measured twice. But in this case, we don't close the horizon. Why? Because when we add up all these angles, it turns out there is a rule for determining the interior angles of a triangle and what they should sum up to. In my previous lecture, I talked about this, and that's the value n minus 2 times 180 degrees. So in this case, we have a 5-sided figure. So 5 minus 2 is 3. 3 times 180 is 540 degrees. And you see here that they missed the 45 degrees by 15 seconds. They came out a little bit low. And something that the author does here for these field notes right here said, okay, is that a reasonable amount of error that I can have? And it turns out that there are different ways of doing this, but one of the most common ways to evaluate if your error is within reasonable limits is to take the square root of the number of opportunities for that error, in this case 5, and multiply it by what you think a reasonable uncertainty is for your angles. And in this case, the person doing these field notes decided that with the instrumentation and techniques they were using, it was reasonable to have a plus or minus 10-second error. So they said 10 seconds times the square root of 5 comes out to 22 seconds. So that would be the maximum error that perhaps you would tolerate. If you got something more than that, you may want to analyze the survey and perhaps re-observe some of those angles. And what it says here in these notes is, okay, the allowable that I have set for myself, the standard is 22 seconds. I came up with 15, so I'm okay. This is a reasonable amount of error, because there's no such thing as a perfect measurement. And then to kind of wrap this up, talk about a couple of things here. One is angles in the vertical plane. So far I've been concentrating on horizontal angles, but when you have the instrument set up, and this is a schematic of the instrument here, you see the tripod and the telescope, you see the horizontal direction, and then you have the inclined direction, which is your line of sight. You can also measure your vertical angles. And as I mentioned in the previous lecture, we have something called the zenith direction, which is exactly the opposite of the nadir direction. So the attraction to the center of the earth, object falls, it's attracted towards the center of the earth, not to the center of the earth, but towards, is called the nadir, N-A-D-I-R, and the direct opposite of that is the zenith. So it's basically a vertical line. And so you're measuring angles now in the vertical plane, and most instrumentation that you use today will actually give you what's called the zenith angle. So you read 0 degrees straight up, 90 degrees looking horizontally, 180 degrees if you were actually observing something directly below, which would be very unlikely. In fact, on most instrumentation that's impossible. And when you have your telescope inverted, so this is in phase 1 over here, but if you invert your telescope, you keep going around, you'll now be reading 270 degrees for the zenith angle. So one of the ways of telling if your instrument is in phase 2 is to actually look at the zenith angle reading, and if it's 270 degrees plus or minus something, then you know it's in phase 2. So one more thing I would like to add here is that if you are sighting a point and you measure the zenith angle, and let's say that zenith angle happens to be 80 degrees, meaning that you are 10 degrees above the horizontal. Not exactly what this picture is showing, you're a lot closer to the horizontal for your line of sight, which it turns out in most cases is actually the more reasonable thing. Keep in mind that when you observe in the reverse position, that you get an angle that would be the equivalent direction over here. Remember, we are 10 degrees above the horizontal line of sight, so 10 degrees above the horizontal line of sight over here would be 280 degrees. So if I write 80, and if I write 280, and I add these up, you notice they come out to 360 degrees. So it turns out there's a check you can do whenever you observe angles, zenith angles in the vertical plane. You take the phase 1 reading, you add it to the phase 2 reading, and see how close they come up to 360 degrees. And we'll talk more about these as we get more into the techniques. I want to stop here by ending with a slide on what I call the care and feeding of a angle measuring instrument, whether that's a transit, a theodolite, or a total station. First of all, they don't like dirt and water. Well, obviously, I don't mean that literally, but letting dirt and water accumulate on them is not good for them. So you keep the dirt, the mud away from them. You similarly keep the water away from them. One of the cardinal rules is you never put an instrument in the case without making sure the dirt has been removed and that the water has totally dried. Now sometimes you're in the field and you have to get it back to a dry place, and that's fine, but as soon as possible you open it up and you let it air dry. I'll talk more about the lens and other glass parts here. That means that you don't generally use it in the rain, although there are a few instruments that have now been designed to be used in light rains or drizzles, and some which can actually work in even heavier rain. Of course, the problem with working in the rain or snow is that your visibility through the telescope is limited because the impact of the rain or the snow on your line of sight through that narrow aperture is highly magnified. You always transport the instrument in the case. So unlike Indiana Jones, who left the instrument screwed onto the tripod and simply tossed the tripod on his shoulder, you do not do that. With a modern day instrument, you always remove it from the tripod, place it in its case to transport it. Whether you're going 20 feet, 200 feet, or 200 miles, you always transport it in its case. When you have the instrument, you either carry it by its handle, as long as the handle was designed to support the instrument, or you hold it by the standards. The standards or the yoke that holds the horizontal axis. The tripod is an essential part of safety as well as support for the instrument to make sure you have a stable instrument when you're measuring the angles. And what I mean by a well-placed tripod is to make sure that it's not in a situation that will cause the instrument to fall to the ground attached to the tripod. And so a really important thing there is to be especially careful when you are on smooth surfaces that are also hard. So concrete, asphalt, things like that, where the points on the tripod cannot dig into the ground, can be very hazardous to your instrument. So having some kind of a slip prevention mechanism is really important. There are various ways of doing that, and some of those will be discussed in lab. Instrumentation should always be handled gently. And what do I mean by that? Well, you don't slam it down on top of the tripod. You don't slam it into its case. You don't jam the case closed if the case doesn't close smoothly. You also manipulate the instrument gently, so you don't crank on the knobs to force it to do something, or to lock it down, or you move it rapidly against a locked instrument and so forth. So you need to be gentle with the instrument. If it takes a lot of pressure to move the instrument, takes a lot of force, probably means that there's something wrong. Always attend. What do I mean by that? Always attend to the instrument. Total stations are anywhere from 10 to 30 or 40 times the cost of an automatic level. They could easily cost more than your annual salary, certainly in a beginning surveying job. So it's very important that you take care of them, and one of them is to make sure that they don't get stolen, that the wind doesn't blow them over, that traffic doesn't hit them, that somebody doesn't steal them, and so on and so forth. That's what I mean by attend. It's particularly difficult with robotic total stations because sometimes you're quite a distance from the instrument. There's many stories where surveyors helplessly stand and watch while somebody stops by an already set up and working robotic instrument, puts it in their truck and drives away. Cleaning. So cleaning of the metal parts of the instrument can be done with a dry cloth or with a lightly dampened cloth. But when it comes to the glass, first of all, if you have dust, you treat it like a camera lens, both the eyepiece as well as the objective lens, and you use a camel hair brush or a bulb type blower to blow off any debris. And if you really have to clean it, you use a lens cleaning cloth or lens cleaning tissue and lens cleaning fluid. Don't sight through the instrument at the sun. This is partly for you. You'll probably burn out your retina, and at that point you will be half blind, and you do it again, you'll be fully blind. But you can also blind the instrument. There are very sensitive electronic components that are used in the electronic distance meter part of the instrument that can actually become overloaded and burn out as well. When you are measuring angles with a large amount of precision, as I inferred already, there can be differential heating and cooling going on in the instrument that can cause inaccuracies in the angle. And so having an umbrella or some other method for shading the instrument is important. These umbrellas and other shade are not for the convenience of the observer, they're solely for the convenience of the instrument. Now, it may turn out that the observer can make better measurements if the observer is also in the shade, but that's a separate issue. And finally, there are very few things, a very limited number of things that are usually covered in the instrument manual that you as a user can do to adjust these instruments. These instruments do go out of adjustment. So this means having to invest more in having a qualified instrument technician, a qualified shop that knows how to work with the particular instrumentation you're using to be able to disassemble them, to repair them, to clean them, or to adjust them. And with that, we will conclude this lecture.